Right, so this is Griffiths Electrodynamics problem 4.28. We've got two coaxial cylinders here. The outside one is grounded, and the inside one is held at a potential V. Of course, the big radius is B, and the small radius is A. And this is being lowered into a vat or something filled with oil, right? It's a dielectric. It has a mass density of rho and an electric susceptibility of this chi sub E. And the dielectric will be forced up into the coaxial cylinders to some height h, and this is what we're trying to find in this problem. Alright, so why is it forced up in? You can think of how the as the oil, the dielectric, moves into this capacitor, the energy is lowered because the electric fields are decreased, because as the oil is polarized, as the charges separate, they partially shield the charge that is on the conducting surfaces, and the electric fields get weaker due to the shielding effect. Alright, so the polarization weakens the electric field inside, therefore lower energy. Therefore, if you take the negative of the gradient of the energy, you get a force, and this is counteracting the force of gravity, which is trying to pull the oil back down. So let's just look at the basic strategy for solving this problem. What we're going to do here is, let's start with, what shall we start with? We want a force balance equation, right? So we want the weight of this oil to balance the force of the electrostatic force as the oil is being pulled up in here. So how shall I write that? Let's just say mg, right, meaning the mass of the oil in here multiplied by the gravitational acceleration is equal to, I'm going to use, what is it? It's equation 4.64. I'll put that at the beginning of the video. This is the electrostatic force on the dielectric as it comes into a capacitor. All right, so 1/2 V squared, and 4.64 you'll see is the derivative of the capacitance with respect to x. In the case of this problem, x is h. X is the distance that the dielectric is being pulled into the capacitor. So I'm going to write the derivative of the capacitance with respect to h instead. Okay. Now this equation 4.64 is a little bit tricky. You get that from the energy stored in a capacitor, which is 1/2 CV squared, excuse me, CV squared, or other ways to write that. But the trick here is you don't want to have to worry about the work being done on the charges by a battery. So you don't hold the potential constant, you hold the charge constant. So you rewrite this as a 1/2 Q squared over C. All right, and then holding the charge constant, you can derive this formula here for the force. Okay. Let's see where we're at. All right. Our final goal will be to get everything in terms of these parameters given to us in the problem, but we'll use some intermediate things such as this little m for mass. We'll of course find what that is. So our question now, I think, right, V is a parameter given to us in the problem, H is a parameter given to us in the problem. We need to know what this C is. So most of this problem is going to be trying to find the capacitance. What is this C right here? All right. Let's write that a little bit. All right, let's start by looking at the potential in the different parts of this capacitor. Okay, so this is just starting from Gauss's law, right? We're going to start with our E dot dl, a surface integral, right? And we don't have to worry about the top of our, if we draw a little Gaussian cylinder in here, like this, you know, little Gaussian surface here, we don't have to worry about the top and the bottom because the fields are going to be parallel to that. So, right, so there's no field going through that surface, they're all parallel. So we only have to worry about the ring around the outside, basic Gauss's law stuff. I'm not sure whether I'm going to actually do that this time. We've done it in so many of the other videos that that I don't know if it's, you know, worth going through all over again. But basically, maybe we'll do a little bit of it, right? If we look at this, you get the magnitude of E, you get a 2 pi. Using the cylindrical coordinates that Griffiths uses, that would be an S variable, right? The distance around the circumference of the cylinder, the Gaussian surface. And then, of course, there's some length, which is the length of our Gaussian surface. This will, however, cancel out because we have some charge density lambda multiplied by that length over this epsilon naught. Anyway, just for once, maybe we'll skip a few of these details, particularly with this displacement as well. We'll see. We'll see. Maybe we can write some of this out really quick. I don't know. It never is very quick, is it? Though. What do we get here? So when we go ahead and make this a vector, put in our little s hat thing, we get this lambda over 2 pi epsilon naught 1 over s hat, and then to find the potential, we are going from this outer cylinder to the inner cylinder, and we have our constant lambda 2 pi epsilon naught 1 over s s hat dotted into the differential length ds s hat. So anyway, the s hats will dot and give you a 1. Oh, it may have actually just been faster to go through all the details. But all right, so when we do this integral, what do we get? And we suck this minus sign into it, right? Lambda over 2 pi epsilon naught, we have the natural log of b over a. Okay, so here's our potential. And if we do the displacement integral and everything, it follows very well. The difference, because we're dealing with a linear dielectric, what we get for that one, let me just write it up here. what do we get? We have a 2 pi, now we have just the epsilon, and this lambda, because this will be a different lambda, we'll call lambda prime. Alright, right, because of the polarization here, you get bound charges along right next to this surface, and it's actually what, like the sum of the bound charge and the free charge down here is going to, as far as charge densities go, that's going to be equal to just the free charge density up here. But way to look at this is if we, these are the same potential though, right? It's a conducting surface here on the inside. They're the same potential, so we can set these two equal to each other. The natural logs are going to cancel out, and the 2 pi's, and we get this free charge density, linear charge density down here below the surface of the oil. That's what this lambda prime is, divided by the permittivity is equal to the free charge linear free charge density above the surface of the oil divided by the permittivity of free space or vacuum. Oh, gee. For linear dielectric, what we have now is this permittivity, right, is equal to, let me bring this over to this side and write it out again. So here's our lambda. This permittivity is equal to a dielectric constant, E sub r, multiplied by the permittivity of free space, which in turn, again, linear dielectric, we have 1 plus the electric susceptibility. Where does this come from? Again, that was from our definition of the electric displacement. All right, for a linear dielectric, this polarization linearly depends on the electric field, all right, with a constant of proportionality of permittivity of free space multiplied by the electric susceptibility, and then we have our electric field, right? So this is for linear dielectric. This gives us epsilon naught. We have a 1 plus this electric susceptibility and E here. All right, and then we call this 1 plus electric susceptibility our dielectric constant. All right, so that's how I just did this up here. All right, where are we in this problem? We are still trying to solve for this capacitance. All right, and to get that capacitance, we're going to just take the charge divided by the potential. And so in order to find the charge, well, let's write this out a little bit. So again, capacitance is equal to the total charge divided by potential. We found our potential, didn't we? Right? We can use either one of these equations and clean it up later. Let's just use this one, right? Since it's got the epsilon naught in it and this original lambda, maybe it will be a little cleaner. So that's our V. Let's look at the Q. All right, the Q is just the sum of these linear charge densities multiplied by the length of each of them. All right. Now let's look at the bottom one first, right? So again, the linear free charge density here on the bottom, lambda prime, multiplied by the length, all right, of this linear charge density section of H, and that gives us the charge on our capacitor for this lower piece. All right, now we're going to add this upper piece. All right, that had a linear charge density of lambda. And how long is this piece up here? Well, that depends on how tall the tube is. I'm just going to call it H, big H, all right? And so the piece up here is just the total height of the tube, big H, minus this little h. So big H minus little h. You'll notice this big H does not appear in the original problem statement, and that is because when we take the derivative, way back here, when we take this derivative, big H goes away. So it doesn't matter at all, right? The height this oil rises, as long as the tube is taller than the oil is going to rise, the height of the length of the total length of the tube doesn't matter at all in the theoretical world. All right, now we're going to divide by this V. Which we said we were just going to go ahead and use this one right here, right? So lambda over 2 pi epsilon naught multiplied by natural log of B over A. Okay, I think we're getting a little bit closer. Let's try and clean up this lambda prime here, right? We found out earlier what this lambda prime was. Did we actually say it? I don't know if we actually said it. Let's solve this equation up here for lambda prime. Okay, so I'm looking at this piece right here and this piece right here, and I'm going to be solving for this lambda prime. So one thing we can do, we see there's a permittivity of free space on each one of these, and then I just need to multiply this up on this side. So what I get is a lambda prime is equal to 1 plus the electric susceptibility, right, this piece right here, multiplied by this lambda. So let's go ahead and add that into our C. Okay, so I'm taking this piece right here and plugging it in up here. 1 plus the electric susceptibility multiplied by this lambda, multiplied by this h, and then plus this lambda h. I should have factored out this lambda, shouldn't I? And then minus this lambda little h right here, and then of course we are dividing by lambda, natural log of b over a, and let's multiply this 2 pi epsilon naught up top. Clean it up a little bit. All right, well, good news for us. We don't have to worry about factoring out this lambda because it will divide out with the ones here on the bottom. And what else can we do? Here, notice we had this 1 multiplied by this h, and then here was a minus h once the lambda is all cleared away. So I can kill this 1 and this h over here. That's a nice mess now. Now we have what's left over. We have this little h multiplied by this electric permittivity plus big H multiplied by this 2 pi epsilon naught all over natural log of b over a. Okay, so I think we've got our capacitance up here. Way back when, we were going to take the derivative of that capacitance with respect to H. So, excuse me, little h, right? So here's where our big H is just going to go away. Alright, so if we take the derivative with respect to this little h, we will just get this 2 pi epsilon naught from right here. We have the electric susceptibility right there, and divided by natural log of B over A. Now, what can we do? Well, we need to put in this V squared and this 1/2. I guess we don't have, yeah, we want to leave it in terms of V squared, so that part's basically done. That's going to be easy. Let's work on mg really quick. G is just going to stay in there, right? The height of our oil should depend on the gravity, right? We move this to Jupiter, it's not going to rise as high because there's more gravity. But we need to work out M really quick. So M is the mass of the oil in that has risen in this tube. Alright? Which is equal to the mass density multiplied by the volume. So there's a rho there. And now we just need the volume of this oil, which is, well, it has a height of little h. And then it's just the area of the big one minus the area of the small one. So that's a pi b squared minus pi a squared. Okay, let's bring out our final answer. So, what we're doing, notice there's no h in this anymore. We're solving for this h now. So, let's write down this equation again really quick. Alright, now we know this m and we know this derivative of capacitance with respect to h. So we're just going to plug those pieces in and solve for little h. So plugging in m, we have a rho h. I'm going to factor out this pi. And then we have a b squared minus a squared. What have I done? I've done just this m part, so we still have to multiply it by g. Now I have a 1/2 v squared, and now I need to plug in, excuse me, I need to plug in this dc by dh, which is just right here. 2 pi epsilon naught, the electric susceptibility thing, natural log of b over a. Okay, well, I see this 2 is going to kill that 2. This pi is going to kill this pi. And that's about it. So let's solve for this h. Final answer coming up. H. What do we have left up here? We have electric susceptibility from right here. We have our v squared from right here, and we have our permittivity of free space right here. And now we just have this natural log on the bottom, and these constants. So rho is left. We got a b squared minus a squared. We have a g, and of course our natural log of b over a. Let me just double check that with what I worked out before, make sure we're not missing anything, and it looks good. I think this is our answer here. So here is the height that this oil will rise. You notice that if I double the voltage between the cylinders, if we go back and look at our picture, right? So if I have a 9-volt battery here, and then I put two 9-volt batteries in there, so doubling the voltage here will make the oil rise 4 times as high because voltage is squared here. What else can we say? It goes inversely to gravity, all right? Inversely to the density of the oil. All this stuff basically makes sense. I'm sure maybe there's some beautiful, deep geometrical things going on with these, the square of the radii here, the difference that. But yeah, there we go. That's the height the oil will rise in this coaxial cable arrangement.